There we go. Okay. So, like I said at the beginning of chapter 12, it was important that we understand kinetics first, because equilibrium is actually based upon the kinetics of reactions, in which you have a balance of the forward rate with the reverse rate in a reaction. That establishes equilibrium. Now, macroscopically, the reaction appears to have stopped, and then the concentrations of the reactants and the products that are left at that point appear to just sit there, and they're doing nothing. But on a molecular level, there is furious activity. The forward reaction is going at a certain rate, the reverse reaction at a rate that exactly balances it. So there are two ways to look at it. And the way to understand the equilibrium, actually, there are also two ways to understand equilibrium too. We can do various equilibrium calculations based on macroscopic principles. And we'll get to them very shortly. Okay, so maybe I should.
Is this part of the, in the last chapter where it said fast, as far as what was happening kinetically?
The rate determining step is the slow one.
Right, it is, but equilibrium is representative of something happening quickly.
Initially, yes. Initially, the rate will be much faster than the rate is after a period of time. Well, we can't say that. No, the rate, that's experimentally determined. And the only thing we can say for sure is that the forward rate and the reverse rate balance one another. That's as far as we can go.
I'm just trying to stay right there.
All right. Just a little bit. Okay. So for this reaction, the Haber-Bosch nitrogen and hydrogen combine to form ammonia. You start off with a certain amount of, well, actually a 3-to-1 ratio of hydrogen to nitrogen. So we have three times as much hydrogen here as you do nitrogen. And then they slowly disappear. And as they do, we accumulate ammonia. And at some point in time, the concentrations of each one of the reactants and products is constant. What you'll notice from, I can do this. I'll try not to write over too far on the left.
All three things are present.
There. I don't know, I might be able to move it back some. How about that? Pick up more. As long as you can still see it, Sarah. There. You notice the reverse reaction here is indicated in a half arrow, a half barbed arrow, and a forward barbed arrow for the forward reaction.
If we're in a state of equilibrium, do you always assume that there are both all reactants and products there present?
Yes, if you can calculate an equilibrium, then yes, there are some reactants still present. It may not be much, and that's not the only case. It could be that there's not much of a product left there either. So that's part of the equilibrium expression. And we'll talk about that in a minute when we get to the law that governs all this. Can you hear everything okay, Sarah?
Yeah.
But
Even Stephanie?
Yeah, I can hear her.
Okay, good.
Sorry.
That's okay.
So, but equilibrium is that the reaction's going both forward and backward at the same rate,
Yes,
or just that it's the same rate?
right. Eventually, they reach the same rate.
Okay. So
The forward reaction and the return
some
reaction.
numerical value of that K being the rate?
Let me think. They would have to be. Yeah, in order for the reactions to balance.
So it doesn't matter how much reactant or product, it's just that rate has reached a steady moment where
Right.
it's going this way.
Yes, forward and backward is perfectly balanced. Now, when we did our calculations in the last chapter, we were interested in the rate up here. That we just said that. The definition of chemical equilibrium. This is another way to represent them. The forward rate is extremely fast in the beginning, and the reverse rate at the very beginning is 0. That's why we used in kinetics the method of initial rates, because there was no competing reverse reaction. We were only judging the forward reaction rate. But if we let the reaction proceed, the forward rate decreases, the reverse rate increases until they meet. Then you have an equilibrium situation where forward and reverse are the same. Okay.
Is this pretty common though? Like when you have water and carbon monoxide turning into just diatomic hydrogen and carbon dioxide, like is that just naturally occurring, or are there certain conditions under like that just happens?
Oh yeah, definitely. You have to set the right conditions, right? And since they're all gases, this has to be an enclosed vessel, a sealed vessel, because you don't want any unknowns, reactants from the outside or products from the outside influencing the reaction.
So, but in just nature, like just not being in laboratory enclosed conditions, is there an example of this happening, or is it always a contrived
It
laboratory?
I don't know. The natural setting is so complex because you don't just have chemistry. You've got biochemistry too. The microorganisms will be involved in these types of reactions with their enzyme systems. And it just makes it too complicated to deal with. You have to control the situation in order to study it. So these reactants are placed in a closed vessel, and under the right conditions, they produce these products up to a point where equilibrium is established. Now, once equilibrium is established, what happens if you say add more water to the flask? You disturb the equilibrium, right? Because you had reached a point where the balance was established in this forward rate. But if you increase the concentration of water in an equilibrium situation, it's going to tend to push the reaction this direction, right? Because you've got more reactant here. As long as you've got enough carbon monoxide to react with it, and you should have if it's equilibrium, then if you put more water in there, you're going to get the reaction to shift to the right temporarily until it reestablishes equilibrium. You're going to increase the forward rate for a moment, and then eventually the reverse rate will catch up with it and you reestablish equilibrium. At that point, the governing law for this reaction is the same no matter how much of each one you have. Once equilibrium is established, If you add some hydrogen to the other side, it does just the opposite. It pushes the reaction back toward reactants until that equilibrium is reestablished. Now, I've mentioned the law before. It's called the law of mass action. And it was developed in the middle 19th century by these two Norwegians, Peter Weg and his brother-in-law, Cato Goldberg. They were interested in the factors that drive a reaction. So they studied, actually they studied solution chemistry. And they wanted a quantitative way to express equilibrium. Their terms for the rates of the reactions were chemical dynamics, and that's still a valid expression. And equilibrium was chemical statics, because the reaction appears to have reached a point where it just stands still, doesn't change anymore. Now, this is the law that governs any reaction. I'm not too fond of those letters. I like it this way. With the coefficients of small letters, then you can tell where they came from. So this expression is a constant. And you always take the products, and the square bracket means concentration at equilibrium. Right? And then you take the coefficient, and that becomes the power of that expression. So unlike kinetics, where you have to experimentally determine all this stuff, in equilibrium, the balanced equation tells you what the equilibrium expression will be. So you take the concentration of C to the C power, little c power, times concentration of D to the little d power.
And what does little d produce?
That's the coefficient.
Just a coefficient.
Uh-huh. Yep, it'll be a number. And then you take the reactants and do the same thing. Okay.
So the concentration of C at equilibrium to the power to its coefficient multiplied by also the concentration of the product D at equilibrium to its coefficient, now made to an exponent power divided by the reactants. Same sense.
Right. Okay. Now, we know that these have concentrations, for instance, molarity, right? But since these powers can be almost anything, the powers of a concentration could give you an extremely complex unit of measure for this K, right? So typically, the K values that are reported in the literature or in reference manuals will not have units because they're so complicated. It's a mess. It's simpler just to leave the units out and be sure that you've written the expression correctly. And then the K is just given as a unitless number, although we know it does have units. Okay. So before we go to those, let's look at what this represents. If you have basically equal amounts of this and this, and the powers are not too high, that's another if, then the K should be pretty close to 1. Right? Because if you have equal amounts of that concentration, equal amounts of that, then the quotient should be close to 1. It won't always be. And the reason for that is the coefficients have an influence on these concentration figures as you divide them. So that's sort of a rough estimate. But if the reaction favors products, the K will be very large. If the reaction favors reactants and very few products, then that increases the size of the denominator and gives you a small K.
Look at the catalyst, you just asking.
The catalyst does not affect the K. It just happens quicker, that's all. Right. Catalysts have no influence.
So if we had an equation written and we could see that there was one, we just kind of ignore it? Or?
Ignore what, the catalyst?
It just isn't in part.
It depends on the problem you're trying to solve. Okay. If you're trying to get the reaction to produce product quickly, then yeah, you want to know what catalyst it is. Okay. So now that we've written this as products divided by reactants, what if we need to use the equation in its reverse form? We need to invert it. Make these the reactants and those products. What happens to K?
1 over K?
Yeah, it's just the inverse. Yeah, very simple. The inverse of K describes the equilibrium constant for the reverse reaction. If we need to multiply the entire equation by a constant, what does that do to the K? Well, if we multiply it times an n, then that means this n is times each one of these, right? So then we would just have n here, n here, n there, n there. So if we factor out the n, this is K, and that's K to the n. So if you multiply the whole equation through by an n, then that takes the original K to the nth power. Now, why am I bothering with this stuff? Because when we, later on, when we try to combine equations to get a composite equation, we need to know how to do these things, because then you don't just have the equation, but you have a change in your K value, right? And if you know these rules, then you can calculate the K that goes along with the new equation. Okay, oops. Oh, past one.
Since we're using amounts of concentration, so again, that's a molarity measure,
Usually.
but like we're dropping the units, so I guess it doesn't really matter. We just know that it's a molarity, right?
That's the most common unit of measure. But if all of these are gases,
Partial pressure.
you could also use partial pressure, in which case the K would be different. Now they're related. Later on, I'll show you an equation, and I'm sure it's in useful information, where you can relate the K as molarity to the K as partial pressure. And of course, it uses the gas constant.
Does, looking at your next slide here, so what about time? Like, since there's time going by, does it not matter throughout this as far as where you are in the time?
No, once you reach equilibrium, time doesn't matter.
Because it's just reached a constant.
Right.
So it's
Now, time matters between the start and when you get to equilibrium. Some reactions get to equilibrium very fast and some very slow. And that goes back to the last chapter on kinetics. As long as the temperature stays the same, stays constant, the K will always be constant. And it doesn't matter how much you start with, as long as you have plenty of reactants so that one doesn't run out. You know, if one runs out, then, well, actually, if one runs out,
Then you wouldn't reach equilibrium, right?
right. But under certain circumstances, one could be close to running out, but the equilibrium would maintain a certain small amount of that limiting reactant.
Just because the reverse is putting some back in, so just
Yes.
enough to kind of keep it cycling.
Yes. And in my mind, that also adds a factor to the efficiency of a reaction. Right? Because you're looking for product when you're talking about efficiency. And if some of the product is being recycled back to reactants, then the stoichiometric amount that you would expect from the reaction, you can't get it all. Okay, so what we're trying to do in this slide is draw a distinction between the equilibrium constant and equilibrium position. Now, it may seem like splitting hairs, but it's significant. There's only one equilibrium constant. It doesn't matter how much of these you have. Once you reach equilibrium, do the calculation, you're going to get the same constant every time for the same temperature. But if we do, like on the previous slide where we added water or we added hydrogen, we shift the equilibrium position. And the position is relative to absolute concentrations of reactants and products. So you can shift the position, but
So it's just saying you can have a different value of equilibriums based on different sets of concentrations.
Oh, yes.
You can reach it, but
Yes. Is that one registering over there? Okay. All right. So this is a generalized K. Now we have certain situations where we want to define that the equilibrium is an expression for a certain type of reaction. And this is also important because we generally don't put units in for our constant. So sometimes it helps to say, all right, what kind of K is it? Right? The general type of K we have is KEQ. And that equilibrium constant is usually expressed in molarity for each of the components. A very special K is KW. Did we talk about KW in the first? We didn't talk about KW in the first semester. No. Okay. We'll get to that with when we talk about acids and bases. And then also along with that, this Ka, which is the acid dissociation constant. And all you have to do to visualize that one. Let's see. Yeah, better start over. If you take your generalized acid and then you apply equilibrium principles to it, then this acid is going to dissociate in water to produce some protons and what's left over, the conjugate, well, we call it the conjugate base. That's not important right now. But you can write an equilibrium expression for this. Just concentration of this times the concentration of that divided by the concentration of that. Okay? And you would get an AKA for that expression. Okay. Another one is solubility product. So if you have a compound, a solid, that is only very slightly soluble, and usually in water, then you can write an expression for that one, where you have the solid like this, and it dissociates into that, and these are in solution.
Like sodium chloride, is that an okay example?
You could. There are better examples. Only partially soluble. Those that we typically in the past have called insoluble, they're really only slightly soluble. Such as barium chromate would be considered insoluble. Or if we look at, let's see, I have a solubility chart back here. No, don't have one for that one. Or silver chloride. We generally consider that insoluble. But even silver chloride is slightly soluble in water. Okay, and you can write an expression for that. The only thing is, when you have a solid, the solid drops out of your expression. It's not even included because its concentration never changes until it's all gone. So it just drops out. That's why it's called solubility product, because it's just this times that. Right? So the K, SP, is just this for this special case. Like that. Because this will go in the denominator, but it's a solid, so we don't include it. Simply because its concentration never changes. Solid concentration doesn't change because it's not dissolved in anything. We'll hammer that one again later. And then the last one is the formation constant for complex species. We're going to do a lab with that one. And rather than put that one up there and confuse you further, let's just hold it for later.
Why do you have to have a lab with something that has the word complex in it?
Yeah, that doesn't bode well, does it?
No.
And then the KP is a K where you use partial pressures. So all of your components would have to be gases. An extension of solubility product, I use that as a jumping off point. Anytime you have an equilibrium expression and there's a solid involved, it's not included in the expression. Only gas concentrations and dissolved components, soluble concentrations, they're included, but not solids. Or pure liquids. Right, pure liquids are not included. Okay, so in this case, we have an expression for this reaction, right? The Haber-Bosch reaction. We could express it as molarity, and there's your coefficient for ammonia.
What did you call this reaction?
Haber-Bosch. Fritz Haber.
Why is it called that?
Because he invented it. I haven't told you guys that story.
Which thing did he invent?
Oh, Fritz Haber was a chemist, a German chemist, just prior to World War I. And tensions were starting to build around the world between nations. And the non-German nations that were opposed to what Germany was doing, whatever that happened to be, decided to embargo the importation of bird guano from Chile into Germany. Bird guano was a ready source of nitrates, and the nitrates were used to make explosives. Okay, so Fritz Haber, being a good German, decided he would figure out a way to make nitrates from a ready source. And nitrogen in the air, there's plenty of that. All he needed was a source of hydrogen, and you could get that from any petroleum product. You know, natural gas is a good source. So the reaction had been studied in theory in small amounts up to that point, but he wanted to commercialize it. He wanted to make it productive, something that his country could use to make their explosives. So he worked out the chemistry for producing ammonia from nitrogen in the air and hydrogen from some other source.
His marketing slogan was no guano, no problema.
Yeah.
Sorry.
You are being recorded. Anyway, once you have ammonia, all you have to do is oxidize it and you get nitrates. Right? So that was an easy step. This was the difficult step that he figured out. And after he determined how to do that, Bosch came along and improved it. Okay, so in this reaction, we can express it as molarity, right? And there's the powers. Remember, this one is to the first power. That was to the third, that was to the second, and it's based purely upon coefficients. But since they're all gases, we can also express these in terms of partial pressure. Right? So the partial pressure of ammonia, nitrogen, and hydrogen.
And you still use the coefficients as exponents?
Yes. Still use them just like the mass action equation says to. This K will be different than that K because partial pressures are in, say, atmospheres, and this is molarity. So the values are going to be entirely different, but we can relate them. Well, if we do it in terms of atmospheres, you just plug those values in, oops, and you get this value for the Kp of the equation. I might note that, notice this value is extremely large, right? 10 to the fourth. So it favors the production of ammonia under those special conditions. Now, if we know one, and we know the temperature, and we know the change in moles, that is, if you have the sum of the coefficients of the gaseous products, let me write that back up here. Nitrogen plus hydrogen yields ammonia, and we need 2 of these and 3 of those. Then the delta N is going to be the sum of these coefficients, which is 2, minus the sum of the coefficients of the reactants. So minus 4 equals minus 2. So it's okay to have a negative sign in this delta N. You just plug the delta N in right here. So it'll be a negative power for the R and the T. And in this case, since K is written, this K is written in terms of atmosphere's pressure, then we use this coefficient, the 0.08206, rather than the 8.3145, because the 8.3145 is joules. not atmospheres. And the T, of course, always has to be in Kelvin. So you just plug in those values. If you know one and you know these values, then you can calculate that one, or vice versa. Calculate the KP.
So, I guess I'm wondering, what is the benefit of, like, why do you need to know the K? Like, if you have the KP, why do you need to solve for the K? I mean,
If you're interested,
what application,
yeah.
or what importance does it carry there?
If you're interested in doing your calculations in terms of molarity,
Oh, just to switch it over.
then you'd want the other K, yeah.
Okay.
Then you can use it in terms of the same balanced equation, but then your values would be in molarity rather than partial pressure. Or if you happen to find a K in molarity terms, but you're doing your research in partial pressures, then you just make the conversion. Okay, so we calculated this one earlier as the KP, and then we just plug in these values at a given temperature, 35 degrees centigrade in this case, and we get that K. Now,
This is terrible, but can you explain negative coefficient real quick? So what is that?
oh, that's a negative power.
It's a negative power, so like if it's a -2, it's still gonna end up being a positive number, right?
Well, if you have a
Because if you have a negative number times a negative number is a positive, right?
if you have a negative power here,
Yeah.
that's the same as 1 over x to the positive power. Okay.
Let me write this. Told you I need some catch-up math.
Let me think. Let me be sure I've got that right. Let's see.
So it's not like negative numbers, it's like saying it's a.
Hold on a second.
How do you do that on a calculator? Negative coefficient.
Now, wait a minute. I think the negative in.
Oh, here it is.
No, that's right. That's right. The reason I stopped for a moment is I was thinking in terms of this one.
So for example, 3.
If we did that, that's equal to x to the nth root. But the negative power is, yes, 1 over x to that power.
I need a real number, so let's just say, so 2 to the -1 is 0.5.
Yeah, 1/2. Uh-huh. That's right.
3 to the -1 is 0.333.
Right, it's 1/3. Even I have to stop occasionally and try to dredge up old math.
But it's not just me.
Okay, so when we talk about reactions, we can describe them qualitatively as either homogeneous equilibria or heterogeneous equilibria. The homogeneous equilibria is one in which all the reactants and products are in the same phase. So this would be homogeneous because everything is gaseous. Or this would be homogeneous because everything is in solution. Okay? If you have a reaction in which there are 2 or more phases, like this one has a solid reactant making a solid product and a gaseous product, that's heterogeneous. Or this one has liquid water is being decomposed into hydrogen gas and oxygen gas. Those are both heterogeneous reactions. The reason we make that distinction is in heterogeneous equilibria, if you have a pure solid or a pure liquid, those terms are not included in the equilibrium expression. Now for this one, we would tend to write it as, we would be tempted to write it like this. Right? Now the gas, oxygen, of course, does change its partial pressure as the reaction proceeds. But this is a solid, and that's a solid, and their concentrations are fixed. As long as there's any of this one and any of that one, their concentration does not change. Now, the equilibrium position can change the amount of those, but it will not change the expression of equilibrium. It doesn't change the K at all. So what happens is we take these two, and you can look at it one of two different ways. You can say, we just eliminate them. They're gone. And the only thing that counts is this one. But mathematically, what you've actually done is you've incorporated these into this. And since they don't change, they may as well be one. Right? We just assume that's one and that's one. And they go away. Okay? Or just memorize the rule. If it's a solid or a pure liquid, it's gone from the expression. Don't include it. So I mentioned this one a little earlier, the extent of the reaction. You know, how far does it go to one side, or does it stay mostly on the product, the reactant side? Does it make a lot of product, or does it have a lot of reactant still left over at equilibrium? If the K is much, much larger than one, that just means the equilibrium is shifted way, way over toward products, because the product is in the numerator of the expression. So if it's very large, your K is going to be large. And the reaction is generally goes to completion. In other words, you have such little reactant left that you might as well ignore it. I mean, if you're looking for efficiencies. Of course, if you're trying to answer a question on an exam, you can't ignore it. And vice versa. If the K is very small, then the reaction has more reactant than it does product. And the reaction is very insignificant. Now, what if we take a reaction that's a large K and reverse it? Then it becomes a small K. So a reaction that says and if the K is large, then it favors B. But if the K is small, it favors A. But if we reverse the reaction,
which would be 1 over K.
Reverse the reaction, then the reverse reaction is favored, and that one gives you a large K. Right? So you can tell if you have a small K, then that reaction is not worthless. It's useful if you go the other direction. Okay? So if the equilibrium lies to the right, the value of K is large, or much, much greater than 1. And to the left, it's small or much, much less than 1. Now, when I wrote the expression before, I used square brackets. That's the equilibrium concentration. But it's useful if you know the concentrations before equilibrium is reached, or even starting concentrations, then you can do a pseudo K calculation. We call it a Q. Uses the same reaction, but we're not at equilibrium. So if we write the expression rather than K, we write Q, and in that case we use just parentheses to distinguish between the two. And what that tells us is that gives us information so that we can tell which way is the reaction going to move. We know, if we know the K value for this one, and we calculate the Q, and compare the Q and the K, we can tell whether the reaction is going to move toward products or back toward reactants. Okay. The simplest one is if you calculate Q and it's equal to K, then you're at equilibrium. Okay? So test taking. If you're given values, it says calculate Q, and you're also given a K value, you calculate your Q and your Q is equal to K, then you're at equilibrium. You know you're at equilibrium. If Q is greater than K, what does that say? Well, that says that if we're at equilibrium, we have a certain amount of this and a certain amount of that. But if the Q is greater than K, that means we've got more of this than we would have at equilibrium. Okay? If Q is bigger, that means you've got more product than you would at equilibrium. So if you've got more of this than you need at equilibrium, it's going to shift back this way. So that means if Q is greater than K, the reaction shifts to the left toward reactants. And then vice versa. If Q is less than K, that means you've got less of this than you would at equilibrium. And the reaction is going to shift to the right and make more products. So by just calculating Q, we can tell which way the reaction is going to move. Now, why is that important? I know you're thinking that. That's important because when we start doing equilibrium calculations, we need to know which way the reaction is going to move in order to set our unknown values that are going to be part of the solution of the problem. Oh, I've got 1025.
I need a question.
Oh, okay. You need a break?
Yeah. Just
okay. Sure.
How long do these things take?
12, 20, I think, through the lab. You take a break.
I'm good.
Okay.
Now, will I be considered present since I'm like?
Oh, yeah, sure.
Okay.
Thanks for reminding me. I'll make that note right now. Here we go. Have I said anything so far that spins your head around?
Not yet.
Okay, good, good. I wonder if it'll let me pause. Pause recording. Okay. So that's how you calculate Q and what it's good for. Okay. So in this case, this exercise, we have an equation for the reaction of Fe3 plus ions and thiocyanate ions.
Is it thiocyanate?
Thiocyanate. And these are all in solution. Right? So they're part of the expression. You can still see that. All right, so our beginning concentration of the 3 plus iron is 6 molar. So that's initial. And our initial concentration of thiocyanate is 10 molar. And the concentration of the iron 3 thiocyanate ion at equilibrium is 4 molar. So that's an equilibrium. What's the value of the equilibrium constant for this reaction? Well, not answering to my call. So we're starting off with 6 molar there, 10 molar there, and we end up with 4 molar. This is the information that's given to us. So here's the approach. This is called the ICE table. I'm going to erase these and put them back up there. And the ICE table, the best way to use an ICE table, and ICE stands for initial change equilibrium. The best way to use an ICE table is to have your balanced equations set up there above and then build the ICE table underneath the equation. So what are the initial concentrations? Well, we have 6 molar for this one, 10 molar for this one, and 0 for that one, right? Because these are beginning conditions. You don't have any product yet. It's like the initial rates expression. And then the change that occurs is you add 4 molar iron 3 thiocyanate, because that's where the equilibrium is. You've added that much, right? So the equilibrium concentration for that one is 4 molar. Well, what's happened to the other ones? What happens to this one? Well, the ratio is 1 to 1, isn't it? 1 and 1. So that means for every one of these, one of those is lost. So for every 4 of those, 4 of these is lost. Okay? So that's what's left over. You used up 4 of them to make that. The same ratio for this one, right? So you've lost that many from this one. And that means you've only got that much left at equilibrium. Okay? Now that you know the equilibrium concentrations, you can calculate the K. So the K is going to be divided by we just plug in the value because they're all coefficients of 1. Everything's to the first power. So we'll put in this one, and we'll put in this one, and this one. And that's 4 divided by 12, which is 1/3. Okay. So there's your K value for that reaction. Now that we know what the K is, we can use that to do other calculations. So in this trial, at the same temperature, remember, it's got to be the same temperature or the K is not valid anymore. K is different. K changes with temperature. So if we hold the temperature constant, then we can do another calculation where we say start with 10 here and 8 here. And the question is then, what's the equilibrium concentration of the iron thiocyanate? That was a previous calculation. So this one is equal to that expression. Now what happens here? Well, we're not told how much of this we end up with. That's what we want to know, right? So we're going to have to use a little algebra. So the change here is we're going to add some of that. Some of that is going to show up in the equilibrium process. So how much of this is going to disappear? Well, we're going to lose that much there and that much there because they're all 1 to 1 to 1. Right? So this expression is going to be, X is going to be that one. That's going to be the expression for that one. And that expression for that one. Okay? So then we just plug those numbers in. X here, we have 10 minus X times 8 minus X. Let's see. Do I have to do all this calculation or does it do it for me? Good. Okay, so here's the expression that I just put on the board right there. And then if we resolve this expression, we get a quadratic. Right? Remember how to do a quadratic?
No.
Okay.
Not at all.
Okay, so when you have an expression here with x, an expression here with x, in order to resolve that equation, you say this times that is one part right here.
Mhm.
And then this part is this times that is minus 8x, and this times that is minus 10x. Add them together is minus 18x. Okay. So we did this one times that one, and then we did this one times that one, and this one times that one, and add them together.
Hold on, so we did 10 times 8 is 80.
Yes.
Then we did
10 times x is minus 10x, and 8 times minus x is minus 8x. Those both are x terms, so you can add them together, which is minus 18x.
so we were doing
We did this one first, and then we did this one times that one, and this one times that one, add them together, because they're both times x. Here we are. And then this one times that one is a minus x times minus x is x squared. So that's where this expression comes from. We resolve.
because 2 negatives make a positive,
Right.
so now it's x squared.
And then, of course,
Multiplied by our 0.33 that we calculated before is our k.
right, what we've done is in this step, I've taken this one right here and multiplied it by that on that side.
Yeah, I got that part. No problem.
And that's equal to this x.
It was just remembering the order of
Right.
10 times 8.
And then what I've done here is take 0.333 times everything in this expression minus x, because then I take that x over here to make a minus. And that's what's left over. So if you have a quadratic, which is an x squared, an x, and a constant equal to 0, then the solution to a quadratic is this expression.
Where did the 0 come from?
I took this x and I subtracted it from both sides. X minus x is 0, and this side is minus x. You can see how I got there? So if I have this expression, some expression over here is equal to x, then if I subtract x from this one and subtract x from that one, that's equal to 0 here, and this one minus x over here. And that factors in right here. 0.333 times this, and then the minus x also. So this part, 0.333 times 10x, should be 5.99x. And then that x makes 6.99x. Okay?
I'll work through it. So 0 equals that, and you
All right.
and you solved for x, and then x, you had to do a square root in there somewhere because of the squared x.
Not yet. Oh, when we go over here, yes.
Yeah.
Right, this is the quadratic solution. Now, that expression, if we say a x squared plus b x plus c equals 0, then the solution to that, x is equal to minus b plus or minus the square root of 4, let's see, b squared. See, I gotta know my calculator. I'm trying to remember. See if I'm doing it right. Yeah, b squared minus 4ac. So we have this b minus b, and then we have plus or minus square root of b squared minus 4 times this coefficient times that coefficient, all divided by 2 times a. Okay, that's the quadratic solution.
Yikes. Okay.
That's why I write it down on the back of my calculator. so I don't have to remember it. Now, what you're going to get, of course, since you've got a plus minus here, you're going to get two answers, right? So X is going to be some answer or another answer, right? Because you do one calculation with plus and one calculation with minus, and gives you two different answers. Then you got to decide which one is real, which one makes sense. Usually, what one of them will do is we'll tell you X. In this case, say X would be like 25. That doesn't make any sense because that gives you a negative value here. So you throw that one out, and the other one is probably the one you used. Okay. Now, doing this quadratic solution, right, okay, in this case, it was 15.99. If you put X up here, that doesn't make any sense. So it has to be the other one, 5.
So I'm writing down that. It's
Okay.
minus B plus or minus the square root of B squared minus 4AC
Right.
divided by 2A.
Okay. Now, we use this expression when there's no way to simplify. Many equations in this ICE method can be simplified if your K value is extremely large or extremely small. Then the changes in X can be ignored. And that gets rid of the X squared term. Whenever you've got an X squared term, you're stuck with this situation where you have to do a quadratic. But under some circumstances, you can ignore the X because it is infinitesimally small. And you can throw these X's out and just solve that. Okay, that makes it much, much simpler. Have you ever seen that before, Sarah? The quadratic?
Yeah, I have.
Okay.
I mean, I've seen it. It's just been a long time.
Okay. And I'm pretty sure I put that in useful information. That quadratic
25 years
solution.
ago, plus or minus a year.
Yeah.
Sorry. Oh, it's in useful information.
It should be. Yeah, I'm pretty sure it's in there.
It sure is, right there.
Okay. We only use it when we have to. If there's no way to simplify the expression, then we have to go to quadratic. Let's see, what's this one? We've changed conditions, and we're just going to do another calculation. All right, so in this case, instead of 5 molar, it's 3 molar. The equilibrium is the same. Remember, the K is the same. We're just changing the equilibrium position by starting with different amounts.
With trial number 3, we would just do the same ICE chart,
Same ICE chart.
same unfortunate quadratic solution.
Yep.
Okay.
So this is generally how you solve. Of course, you have to have the balanced equation or you can't write the expression. Once you write the expression, then you look at your list of initial concentrations. And what we didn't do here, we didn't calculate the Q. Notice that? We didn't calculate the Q. Why?
We had the K.
No, because we had reactants and no product. We didn't add any product, right? If you don't add any product, then there's no need to calculate the Q because you know the reaction's going to the right. But if you're given certain amounts of every one, and you're not at equilibrium yet with those amounts, then you calculate the Q to determine which direction the reaction is going to go. Because then you would say either it's plus X or minus X as a product. Okay. All right, we're not going to spend time doing this because we don't have the time. At least, well, we have the time, but I want to get on to something else. This is the introduction phase. We can do more of those in the reinforcement during review. Those are your answers anyway. Okay, here's a Haber-Bosch equation. So we're going to take a 2 mole sample of ammonia. Actually, this is the reverse of Haber-Bosch. Notice?
We're decomposing ammonia.
Right. So we put 2 moles of a sample into a 1 liter container. So what's its initial concentration? 2 molar, right? 2 moles per liter. And let the ammonia dissociate. At equilibrium, we find that 1 mole of ammonia remains. So half of it's gone, 1 remains. Calculate the value of K. Oh. It's not going to do. Okay. So you would take the ammonia, yields nitrogen and hydrogen. There's to balance it. So we need 2 of these, 3 of those.
So
What's the, yeah. The initial concentration then is 2 molar.
I guess I just wouldn't have known to balance the equation. Like, so on the test, will we be given a balanced equation, or are we going to need to balance?
Could be either one. So you do a quick check. Look here, it's obvious. There's only 1 nitrogen here and 2 on that side, so you got to balance it. So what's the change? We know that we're starting off with 0 here and 0 here. So we're going to end up with some over here, aren't we? All right, we're going to end up with, we're going to make some of that. And for every 1 of these we make, how many of these do we make? 3, right? And we're going to lose, for every 1 of these, we lose 2 of these. All right, so we got 2 minus 2x, and then we have x. Okay, I'm complicating this a little more. We're actually told that the equilibrium is 1 mole of ammonia remains. Right? So this one is equal to 1 molar. So how did we get to 1 molar? We lost a molar, right? We're given this, so that means we lost 1 of these. So for every 2 of these, we lose 1 of those. So that means we lost half molar. I mean, we gained half molar on this side. And for every 2 of those, we gained 3 of these. So that means this is 1.5. Well, how do I know that? Well, if this is what we lost from here, it's going to show up over here. The ratio is 2 to 1. So if this is 2, this represents 2, then 1 is represented by 0.5. 0.5. And for every 1 of these that shows up, 3 of these show up. So 3 times that is 1.5. Okay. Okay, now we can tell what our equilibrium concentrations are. And then we can calculate K. So we have nitrogen to the first power. We have hydrogen to the third power. And we have ammonia to the second power. Okay. And that should be 1.69.
So it's products divided by reactant.
Right.
So in this case,
These
it's
two. That power.
the concentration of nitrogen is 0.5. No power, coefficient is 1, multiplied by hydrogen is 1.5 to the third power, coefficient is 3, divided by ammonia, concentration is 1 mole, the second power because it's coefficient 2.
Okay? Is that right? 1.69?
Yes, that is correct.
Okay. All right. Okay, we got a different one here. Where do we stand in the grand scheme of things here? Let's see. We're good. So we can take time to do this one. We need a new equation. N2O4, dinitrogen tetroxide. And NO2. That looks like it's balanced. So we have 1 mole sample in a 10-liter vessel. So 1 mole in 10 liters is equal to 0.1 molar. Okay? And we're starting off with 0 product. We're given the K. We have K is equal to 4 times 10 to the minus 4th. Minus 4th, which is equal to NO2 squared divided by N2O4. Okay. So if we start off with this, we end up with that, the reaction has to go this direction because there's none of that. That means we're going to add, well, actually, what's the question? Calculate the equilibrium concentration of N2O4 and NO2. Here's where you have to decide, what are you going to let be equal to X? Usually you try to let the X be equal to the answer, so you don't have to do any further questions once you find out what X is. So if we let X equal this, then that one is 2 times X, because it's 1 to 2. Whereas if we let this one be X, that will be half X. So you have to go through some mind gyrations to get that one. So I would say let this one be, change is you're going to lose some of that one. It's going to show up over here, twice the amount. So that means this one is 0.1 minus X, and this one is still 2X. Okay, and that expression is equal to 4 times 10 to the minus 4th, which equals to, 2x squared over 0.1 minus X. Okay. So Let's see if we can simplify this. If this is 10 to the minus fourth, that means very little of this is going to show up. Very small. Well, we can't let x equal to 0, then our expression would be infinity. But if this x is 0, it's so small we can ignore it, then we can approximate this one as 4x squared, which is the resolution of that one, divided by 0.1. Okay? That would simplify things. Then we wouldn't have a quadratic. Because if we leave this one here and move it over here, then we're going to have to move this one over there, and now you've got an x squared, an x, and a constant that you have to solve quadratically. So if we let this one be equal to 0, that was very small, then we can take this 0.1 and put it over here, and that means 4.0 times 10 to the minus 5th, right? Because that's 10th times this. And that's equal to 4x squared. Then x squared is equal to 4 divided into this, which is 1, times 10 to the minus 5th. And then x equals the square root of 1 times 10 to the minus 5th, which is equal to square root. So I get 3.16 times 10 to the minus third would be this one. Now, in order to verify that this is a valid number, and we didn't make a huge mistake by saying that's equal to 0, then what you do is you take your equilibrium calculated values and you plug them back in your expression and see if it equals this. Right? So if that's x, wait a minute. No, I'm not finished yet. That's x, but the concentration of this one is 0.1 minus x. See that? Okay. So 0.1 minus x then would be that value subtracted from 0.1, which is 9.69 times 10 to the minus 2 for this one, and 2x would be that one. Times 2, which would be 6.32 times 10 to the minus 3. Okay, so now what you have to do is plug this value in here, here, square it, and then divide it by this value. And when you use those values, K is calculated at 4.12 times 10 to the minus 4. Okay? So it's very close, right? But we need a quantitative way to say it's good enough. So we use the 5% rule. Is it within 5%? So what's 5% of that? 4 exponent. There. And 5% is 0.05, isn't it? Yeah. So since this one's high, we're going to say 1.05 times that. Right, to add 5%. Add 5% to this. And 5% is, so that's good. It's less than, this is plus 5%.
I gotcha. I guess my question is, like, from the very beginning, it's like just choosing to make X 0 there, the very first step. Like, why did you do that? How did you know that was okay to do? Like, why would I feel compelled to do that?
Okay, it all goes back to this value right here. Since this value is very small, it means that we're not going to make much of that. In other words, we're not going to make much of this, and we're not going to lose much of that in the process. Right? It's going to be a very small number. So since it's very small, you eliminate it from here. Why? Because if you eliminate it from there, you got 0 divided by a number's infinity.
So we're not using 0 to represent X. We're just going to take that part of the equation out as insignificant.
Yes, we're going to eliminate. See, that's why I used approximately. Yes. Yeah.
And you only chose to do that just because of that K value being so small.
Right. And
just saying, for the sake of easier math, let's just do this.
if I resolve this equation over here, then this times 0.1 minus x equals 4x squared. And then 0.1 would be 4 times 10 to the minus fifth minus 4, 10 to the minus 4x. Oops. And we'll move this one over too. Minus 4x squared equals 0. Now you can solve that quadratically. Okay? There are three ways to solve one of these equations. Quadratically, estimate by eliminating a factor that would complicate the quadratics, because if you get rid of that, then you put that one over there and you solve for the square root. This term that messes things up. Or actually, it's having both of them in the same expression, an x and an x squared. If you only have an x squared or you only have an x, life is great. But you can solve it quadratically. You can eliminate the x, solve it, and compare it to make sure it's 5%. Or, let's see, there's one other.
Why is 5% the rule of thumb for this?
It just is.
Like within an acceptable.
Yeah, it's statistical. Yeah. The other thing you can do is, if you make this change, then you can take these values and plug the x values back in here. Say, plug the x back into here, and then solve for it again. And you get a number that's even closer to that. It's called successive approximations. So you go through several, sometimes it takes 3, 4, 5 iterations, but eventually you get to a value that's under 5%. And sometimes it's easier to do that than to solve the equation, especially if your equation comes out not quadratic, but cubic. You know, if it's cubic or worse, then, well, there is a cubic solution, but it's a nightmare. Sometimes you would have to use matrices to do it. So the successive approximations is usually the easier way to go. Okay? All right, so that one's solved. Clouseau would say.
What show is that from?
Pink Panther.
Oh, right.
The crime is solved. Okay, so let's go to the next one and see what we got.
Oh, man.
See, that's true. Okay. Now, we sort of alluded to the Le Chatelier's principle earlier, and this is going to be the guiding principle for next week's lab. Le Chatelier's principle. I know it doesn't say so in the title, but down in the body of the lab. And this one doesn't have a formal report required. You just do the exercise, answer the questions in the hard copy, and turn that back in. Le Chatelier's principle says, if your system is at equilibrium and you do anything to disturb it, it will respond in such a way as to mitigate that disturbance. So the way we did it earlier was we added some water. And that disturbance caused a response that would drive the reaction to the right until it reached equilibrium again. Or you added hydrogen to the right and it went back to the left to use up some of that hydrogen and it's reestablished equilibrium. That's Le Chatelier's principle relative to changes in concentration. But that's not the only disturbance you can do to an equilibrium state system. That was concentration. But what if we change the temperature? A change in temperature for a system is a disturbance, but the piece of information you need to know about that reaction is it endothermic or exothermic? So here's what I mean by that. If we have a reaction and it's endothermic, then heat becomes a reactant because you're storing heat into the products. That's an endothermic reaction. Okay, so let me identify that. Endothermic. We make heat a reactant. So for endothermic reactions, if you increase the temperature, where does that show up? Right here. You add heat to the reaction, it's going to drive the reaction to the right. That's an endothermic process. For an exothermic reaction, heat is a product. So an exothermic reaction puts the heat on the product side. Now if you increase the temperature, you drive the reaction back toward reactants because you're inputting something. This system is at equilibrium already, and if you add heat to the reaction, you're going to drive it back toward products. That's the problem that Haber had with his, Fritz Haber had with his reaction, where he took nitrogen and hydrogen and made ammonia. That reaction is exothermic. So he wanted to be sure that he had met the activation energy for the reaction, so he increased the temperature to like 400 degrees centigrade. Well, the problem with that is it gave him activation energy for the reaction, but it also added heat and drove the reaction back to reactants, so it kind of defeated the purpose. So he solved the problem. He solved one problem thermodynamically or equilibrium-wise, and then he solved that problem that he created for himself with a catalyst. So if you increase the temperature and you add a catalyst, then it speeds up the reaction in that direction. It doesn't change the equilibrium, but it speeds up the reaction in this direction. So it produced product, a small amount of product. And then what he did was, the product was ammonia. The reactants are nitrogen and hydrogen. So their condensation temperatures for nitrogen and hydrogen are much, much lower than ammonia. He only had to cool it a little bit, and the ammonia would just rain out of solution, or rain out of the gas. And then he would just take all that stuff, cycle it back around through the catalyst, and you do that 5 or 6 times, and you increase your overall efficiency to like 90%. That's how he solved the problem. Concentration, temperature. Okay, pressure. Pressure, if you change the pressure for a reaction, what do you need to have any response at all? You've got to have a gas. Pressure has no influence on solids and liquids, right? So if your reaction has no gases as reactant or product, then pressure has no effect at all. But if there's a gas in there, then what you get is the system will shift. If you increase the pressure, the shift will be such a way as to reduce the number of moles of the gas. Or it will change the balance of gas. Let's say we have, let's take copper again. Nitrogen gas and hydrogen gas yields ammonia gas. Okay, so we need 2 of these, 3 of these, right? So how many moles of gas do you have on this side? 4 moles. On this side you have 2 moles. Okay. So now, if this system is at equilibrium in an enclosed container, and you change the pressure, either by injecting an inert gas or by changing the volume. So if you decrease the volume, you'll increase the pressure. So if you increase the pressure, how is the system going to respond? Increase the pressure, the system will respond to reduce the number of moles of gas. So you increase the pressure, and if you put a gauge on it and watch the pressure change, you increase the pressure and you see the pressure go up, and then as the system adjusted, the pressure will come back down some. Because it's taking this and shifting there. You make fewer moles of gas as a response to increased pressure. So if we expand the volume and decrease the pressure, the response will be back toward more moles. Right? So that's another thing that Haber did. He put these gases under lots of pressure too, several atmospheres. And that favored the production because he knew about Le Chatelier. He knew what would happen to the reaction. Oh, I misspoke. You add an inert gas, it has no effect on the equilibrium. So only changing the volume. Now, we could change the pressure by just adding more of these gases, right? But then you could approach it from this way, or you could approach it from the concentration side too. You're increasing the partial pressures of each one of these, which drives the reaction that way. So they sort of intermingle.
Le Chatelier's principle requires that a chemical system respond to atomic stress. If reactant or product molecules are added to a system at equilibrium, the system will shift toward the side opposite of the added component. If a reactant or product is removed, the system will shift toward the side of the removed component. Let's consider an example of a system at equilibrium, the reaction between iron and thiocyanate to form iron thiocyanate. Iron 3 is a light-colored ion in neutral or slightly acidic solutions. Thiocyanate is a colorless ion in solution. The iron thiocyanate complex is a blood red ion. The reaction of iron and thiocyanate in solution is reversible. That is, it moves in both the forward and reverse directions. Let's consider what happens to the reaction when changes are imposed on the system. In which direction will the addition of iron 3 nitrate shift the equilibrium of this reaction? Observe what happens as iron 3 nitrate is added. The equilibrium shifts toward the product, since the iron 3 nitrate is a source of iron 3 ions, one of the reactants in our equation. As a result, more of the iron thiocyanate ions are formed and the solution turns redder.
Okay? So what is nitrate in that reaction?
Just a catalyst.
Mhm. Remember when we wrote complete ionic equations and molecular equation, complete ionic equation, and net ionic equation? Nitrate is a spectator.
Oh,
Right. It just sits there and watches.
it was just
The equilibrium between dinitrogen tetraoxide and nitrogen dioxide is dynamic. As shown, N2O4 molecules fall apart at the same rate that NO2 molecules recombine. If we change the equilibrium conditions, the equilibrium concentrations will shift according to the Chatelier's principle. As we increase the temperature, the equilibrium shifts to the formation of additional NO2 molecules.
So that must be an endothermic reaction. Because if you add heat, it's as if you're adding reactant and drives the reaction toward product. Now, when I say right and left, that only has value if I've also got the balanced equation in front of me, right? Because right and left could be something else if we reverse the reaction. So when you say right and left, say you're completing your lab, you want to have that balanced equation there. So if you tell me right, left, I know what you mean. Otherwise, shift toward product, blah, 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 say what it is.
Yeah.
I think that's it, isn't it? Yep.
good, because my brain is.
Yeah. We fried Stephanie's brain. It's time to quit.
Yeah.
So I'll convert this to an MP4 file and put it in Blackboard. So you can go back and look at it again if you want.
And enjoy my bad joke.
Oh yeah, the joke's gonna stay. Okay?
All right.
Hope you feel better, Sarah.
Thank you.
Let's see here. Stop the recording.